Okay, see, last time we have discussed this topic of mean fluid temperature and mean plate temperature, because these are the temperatures which are required to calculate the overall heat transfer or heat loss coefficient, and also to calculate this convective heat transfer coefficient of the fluid flowing through the pipe. Because to calculate this convective heat transfer coefficient, we need to evaluate the fluid properties, and those fluid properties needs to be evaluated at the mean fluid temperature, that is the temperature of the fluid flowing through this solar collector. But of course we know that this temperature is continuously changing from inlet to outlet, so we need a mean value which can be used to estimate all those thermophysical properties of that particular fluid which is flowing through this solar collector. Thermophysical properties of the fluid which are normally required are normally density, viscosity, and thermal conductivity. Right, so the derivation of this equation 4.39 was not done, so now we shall do the derivation, the complete derivation of this equation 4.39, and how this mean fluid temperature is actually calculated. It is based on this integration formula. So we have to integrate this fluid temperature in the y direction. Y direction is the direction in which the fluid is flowing, and this is the equation. The temperature of the fluid at any y can be calculated from this equation. This equation we have already derived in the previous lecture. So now we shall be using this equation to derive the mean fluid temperature using this equation. So where we are actually integrating this equation of fluid temperature at any y from 0 to the maximum length L of that solar collector, and then we divide it with the length L of that solar collector to find out the mean fluid temperature. So now this is the starting point to derive this equation 4.39. So next we shall start the derivation of this equation 4.39 from this equation of 4.33a. Right, so here is the equation which we will be using to derive that equation 4.38. So here in this equation, this equation is the fluid temperature at any y, so in the flow direction, in other words. So in this equation we can see that these are the terms which are constants: the inlet fluid temperature, the ambient temperature, the absorbed solar radiation S, which is also a constant at a particular instant, and also this overall heat loss coefficient for a certain plate temperature and ambient temperature when those are fixed at a particular instant. So this UL, the overall heat loss coefficient, is also constant or not changing at that particular instant of time. Then N represents the total number of riser tubes, W is the spacing between two tubes, and F dash is the collector efficiency factor, which we have already discussed and derived also. M dot is the fluid flow rate, and Cp is the specific heat of the fluid. So all these terms in this equation 1, which I have shown, are actually constants, and they are not changing with respect to y direction, because we are interested to find out the mean fluid temperature in the y direction. But in this particular equation, all these terms are actually a constant. So here we shall now rewrite this equation in a certain way so that we can derive it to an appropriate form. So now in this equation, let me define two new terms. So here we can define this constant EFI minus DA minus S by UL, this whole term. This whole term is given the name alpha. So let alpha is equal to TFI minus DA minus S by UL. Similarly, we define another term beta or B as this one. This whole term UL into N into W into F dash divided by M dot CP, except Y. These are the terms which are actually a constant. So this is defined as another constant B or beta, and this is defined as constant alpha. This whole term, this denominator term. Here the TF is the fluid temperature in the y direction, which is changing. So that is a variable. So this TF makes this whole term a variable. Similarly, here in this on this side, this y makes this whole term a variable, but we are taking separating this term and represented by beta, right? So now from this equation 1, this side, the left hand side, can be written like this one, because in the numerator TF minus TFI, add and subtract TFI in the numerator, right? So the rest of the equation is same. Next, here what we have done, we have introduced this term alpha. So this whole term is defined as alpha, and here in the numerator again we have this TFI minus TA minus S by UL, which is defined as alpha. So the numerator becomes TF minus TFI plus this whole term, which is defined as alpha, and this whole term is also alpha, right? So now further we can simplify. Alpha is divided with this TF minus TFI, and alpha is divided with alpha, so it becomes 1, right? So now let's proceed further. So now this equation 1 can be written in terms of this alpha. So this whole term can be replaced with this new term, right, in terms of alpha. So now this equation 1 becomes, this side is actually equal to TF minus TFI divided by alpha plus 1, and on this side this whole term is defined as B or beta. So this is the new form of equation 1. So now further we can write this equation in terms of TF, right? So TF is equal to TFI minus alpha plus alpha. So this is a simple mathematical step which you can understand. So here we have the equation of TF. In this equation 1 is written now in this form, which is equation 2. So now the mean fluid temperature, we will proceed further from this equation 2 onwards to find out the mean fluid temperature. So now the mean fluid temperature TFM can be estimated from this equation, right? And we already know this is the general equation to calculate the TFM, where TF at any y is this equation 2, right? So now we can put this equation of TF here, right? So this TF is replaced with this equation, right? So this whole equation TF at any y is replaced with this one, and actually we need to integrate this equation. So because this TF represents TF fluid temperature at any y, because y is a variable, right? So TF at any y is replaced with this equation, right? So now we have this form, which is to be integrated. Now here again notice that in this equation TFI and alpha are constants, right? So let's proceed further. So here TFI and alpha are constants with respect to y, actually, because y is the variable. So that is mentioned here. So now we shall further rewrite this equation. Here TFI minus alpha is written separately, that is a constant that is separately written. Then 1 over L is multiplied with this term separately, alpha into exponent of minus by into dy. So now this is the next step. Now we shall do the integration. So here this term is constant, so that is taken out, divided by L, 0 to L, integral of, now what is remaining, only 1 into dy plus 1 over L. This term is written as it is. Now here this integration will be simply y, so this term will be simply y, and limits are applied from 0 to L, and that term is written again, same as in the previous step. Now in this equation, the alpha and beta both are actually constants with respect to y. So here again alpha and beta are constants with respect to y. So now we shall integrate this part in the next step. So here is after integration. So after integration of this term, exponent of minus b into y, so that will be exponent of minus by into minus 1 over beta, because that is the integration of this term, exponent of minus beta y. So that is shown here after integration and applying the limits 0 to L. Right, so here is this form of TFM. Now further 1 over L is taken constant, so inside what is remaining, TFI minus alpha into y minus alpha over beta, exponent of minus by 0 to L. Next what we will do, we shall apply the limits L and 0. So first we shall apply the limit of L. So y is replaced with L, and here is again y is replaced with L, and minus, now we shall use this 0. So this 0 is replaced with y, right? TFI minus alpha into 0, and here again it will be plus alpha over beta, exponent of minus b into 0. So now limits are applied. So next we shall solve it further. So now what we have here, TFI minus alpha, this L will be cancelled with this L, minus alpha over beta into L. This L is multiplied with this one, right? Here this term will be 0, and this term is also written here, exponent of minus beta into 0 will become 1, because this is e to the power minus beta into 0, so e to the power 0, which becomes 1. So what is remaining, alpha over beta into L, right? So this is now the equation 3. Okay. Now we shall do some further manipulation. So we will come back to this equation 3 again. So this is because here again this is not the form which we require, because now there are alphas and betas, so we have to replace those alphas and betas in such a way so that we can have the desired form of equation 3. So this is equation 3. We shall come back to equation 3 again. So now first of all we will deal with alpha and beta. So here we have the term beta into L. Here again beta into L, and we already defined what is beta. So and also we shall introduce this term that N into W into L represents the area of the whole solar collector, where N is the number of tubes, W represents the distance between the center of those parallel tubes, then the area of the whole collector is given by N into W into L, right? So we shall introduce this term AC in this equation, because we already have defined what is B or beta into L. So now here in this equation, N W into L represents the area of the solar collector. So we have separately written NW into L, right? And that is the collector area. So this is now equation 4, right? So in this equation 3, beta L, here beta L can be written in this form, right? Because now we have replaced what is beta and multiplied with L, and that gives another term, the collector area, the whole collector area. So now this is equation 4. So we shall put it in equation 3, but before doing this, we will further do some manipulations, and then we shall come back to equation 3. So remember this equation 3, and now we have one more equation, which is 4. We have also derived this equation of F double dash collector flow factor. We said this was collector flow factor, which is ratio of collector heat removal factor and collector efficiency factor, and this equation we have already derived. So now in this equation we can, this term is actually beta, 1 over beta, which we have defined. What was beta? This one UAF dash over MCP, and here we have UAF dash over MCP. So that is 1 over beta. So this term is actually 1 over beta. So we can introduce this 1 over beta into L. Actually it is beta into L, which is UAF over M dot CP. So in this equation, that represents 1 over beta L. So F double dash is equal to F R over F dash, and that is 1 over beta L, 1 minus exponent of minus beta L. So this is equation 5 now. Further, we can simplify this BL into F dash. So take this BL to this side into F dash is equal to 1 minus exponent of minus B into L. So here further we can write this exponent of minus B into L is equal to 1 minus BL into F double dash. Okay, so now this is equation 6. So remember all these equations 3, 4, 5, 6. Next we also have derived this equation of heat gain of the solar collector in terms of inlet fluid temperature with the introduction of this factor, collector heat removal factor FR. So this equation we have already derived, and we know what is this equation. Okay, so now in this equation we shall further simplify this equation. QU divided by AC into FR is equal to S minus this one. And if we take minus on this side, if we take minus common from this side and put it here, then it will be minus QU over ACFR, and here it will be minus S over, now here UL is also taken common from this whole equation. So S by UL, and this will be TFI minus TA. All right. So here the minus was taken out and that was transferred here. So this step is hopefully clear. Now what is this term? We have already defined this term as alpha, right? So if you go back to the previous slides or the previous video clip, so you will see that we have defined alpha as TFI minus TA minus S over UL. So we have replaced. So now alpha can be written in terms of this term, which is QU AC and FRUL. Right. So now this is equation 8 now. Right. So now we have so many equations which we shall now use in the equation 3. So I told you that we will come back to this equation 3, which we have already derived, of TFM is equal to TFI minus alpha over beta. So here we shall now further by putting the values of alpha and beta, we shall have the desired form of TFM. So here we shall further simplify this equation. So here alpha is taken common from these three terms. So this alpha is taken common into 1 over BL minus 1 minus 1 over BL exponent of minus BL. Right. So now substitute this exponent of minus BL from equation 6. It was equation 6. This was equation 6. Exponent of minus BL is equal to 1 minus BL f dash. So in this equation, we shall replace this term with 1 minus BL f double dash. Right. This is we have already derived separately from equation 6. Right. Let's go further simplify कर लें. So that is dfi plus alpha into 1 over BL minus 1 minus 1 over BL, which is multiplied inside here. So this BL will cancel with this BL, and what is remaining f double dash. All right. Further simplify this 1 over BL, and 1 over BL will cancel. So what is remaining? dfi plus alpha into f double dash minus 1. Right. So that is dfm is equal to this simple term now, because this BL is been cancelled with each other. So now we can finally substitute the value of alpha, right, from equation 8. What was equation 8? This was equation 8. Alpha was defined initially like this one, and then this value was equal to this one from this equation 7. So in other words, alpha is equal to this term. So now we shall put this value of alpha here in this equation. So alpha is replaced with this term. Right. So now this is our desired equation of mean fluid temperature, which we can calculate with the knowledge of QU, AC, FR, UL, and F double dash. So this will be an iterative procedure to calculate this TFM. Initially we shall assume TFM, and then TFM will be. And on the basis of this TFM, we shall calculate QU, UL, and then we shall iterate this TFM with this equation. So the same equation is further written in this form. Here it is written as 1 minus f, and this minus will be this will make this plus. So this minus becomes plus, and that is the desired equation. Here QU divided by AC is written separately in the numerator divided by f. So that is the equation which you see in the book, right? So here is the complete derivation which we have done to calculate the mean fluid temperature of the fluid flowing through that solar collector. So that was the desired equation. Okay. So the next topic is critical radiation level. Right. So what is meant by critical radiation level? Radiation level where the absorbed solar radiation and lost terms are equal. We know what is absorbed radiation. Absorbed radiation is given as S, which is actually G into tau alpha in general, right? And we of course know that this G has further 3 parts, and tau alpha also has 3 parts for beam, diffuse, and reflected radiation. So that is the absorbed radiation minus what is the lost term. Lost term is U, defined as U into delta T. Right. So what is critical radiation? Radiation level when this absorbed radiation becomes equal to this lost term. So when this will happen, when this the available and absorbed radiation and the losses are equal, it means, because this S minus U delta T represents the heat gain, useful heat gain. So in other words, we are saying that this will be 0 when the available radiation and the loss radiation both becomes equal. Then this term becomes equal to 0. There is no useful heat gain. It means the solar available radiation is so low, or in other words, the losses are too high, So then this could be a condition at which there is no net useful gain of the solar collector fluid, right? So that is defined, and so that particular radiation at which this occurs, this condition will be occur is so corresponding to this condition. When this QU is equal to 0, corresponding to this condition, whatever is the available solar radiation, that is known as critical radiation level, right? So by putting this term, this whole equation equal to 0, we can find that condition, right? So this is our equation. The useful heat gain in terms of inlet fluid temperature, right? So critical radiation can be defined as by putting this QU equal to 0. So by putting this QU equal to 0, we can write this equation in terms of G, T, the available solar radiation on a tilted surface. And because QU is equal to 0, so that radiation is also known as critical radiation, GTC, and that is given by this equation 4.38. Right. So collector can provide useful output only when the available radiation, G available, is higher than this value, right? Higher than. So our available solar radiation should be greater than this value, because this is the critical radiation. It is the minimum at which the QU is 0. So the available solar radiation should be or must be greater than this value, which is given by this term, right, to have some useful output QU, or QU will be greater than 0 only when this available solar radiation is greater than this value. So it means now we have one in the form of equation. What is the critical radiation level, right, based on which we can design the pump of a system, or we can control the pump of a solar collector loop, because we can design our pump on the basis of this equation 4.38, that whenever the available radiation is greater than this value, only then the collector pump should be switched on. So here is our solar collector, which is connected to an application or a storage device, and here is this pump. So we can control the function of this pump on the basis of this equation 4.38, right? So whenever this the available solar radiation, G available, which we can measure with the help of a pyranometer. So for example, here is a pyranometer which is measuring this radiation, available radiation. So whenever this available radiation, G available, is greater than G critical, which is given by equation 4.38, only then this pump should be switched on. So there is a control system which is measuring this G available, comparing it with G critical, and after comparison, if this term is a positive value, means G available is greater than GTC, only then it will make this pump to on, because only then we have some useful output or useful heat gain, right? So that could be a strategy to control this the functioning or operation of that pump, right? And we already know what are UL, what is FR, tau alpha, inlet fluid temperature, ambient temperature. So all these terms are clear to us because we have already learned about them in this chapter. Right. So collector output can be written. So the same equation 4.37 can be written in terms of critical fluid temperature. So we can introduce this GTC here in this equation. So after one or two mathematical steps, we can write the same useful heat gain in terms of available solar radiation and in terms of critical radiation value. So we can introduce this GTC here, right, by separating this term FRULTI minus TA. So TI or TFI means the same thing. So we can write the same equation 4.37 as 4.39. So 4.39 indicates that for a collector to produce this useful output, QU should be greater than 0, means absorbed radiation GT into tau alpha must be greater than the thermal loss time. So the controller can be designed. I have already explained this last sentence here with the help of this figure. Okay. So let's proceed to the next topic, which is the thermal analysis of air. So the solar air collectors are quite similar to the liquid solar collectors. So here we shall be studying the same flat plate type of air collectors. The major difference will be that now there will be no closed pipes or small diameter pipes through which this air can flow. Instead, we need a larger area for the air to flow because air occupies more volume compared to liquid water or the liquid solar fluids. So that's why in case of air collectors, because it is a gas which occupies much larger volume for the same amount of mass, so that's why we need a larger flow passage in case of air collectors. So the schematic diagram of typical air solar collector, air type flat plate solar collector is shown here in this figure. The air passage is this one. So here is the glass cover, the top one. There could be again more than one glass covers. Then there is this absorbing plate which absorbs the solar radiation, and at the bottom of this absorber plate there is that air flow passage. So this whole area is actually open for the air to flow, right? So this passage is actually a narrow duct with the surface of the absorber plate is actually at the top, is acting as a top cover for this air, right? And similarly there is another back plate at the bottom. So between these two plates is this air is actually flowing, and behind this back plate there is insulation to prevent the heat loss from the back of that plate, right, or from this plate, because maximum heat we would like to be transferred from this absorber plate to air, and minimum should be transferred from the back side. So that's why there is, just like in the liquid flat plate solar collector, here we have the insulation, right? So that is one typical type or one simple type of air type air type flat plate solar collector, right? The thermal analysis of this type of solar collector is very much similar to the liquid flat plate solar collector. The major difference will be there are no fin efficiencies, because there is no pipe connected to this plate, and because in case of liquid collectors there were pipes like this one in which liquid fluid was moving, and this portion between the two pipes was acting like a fin. So here there is no such fin efficiency required, right? So that's why we can raise it. There are no pipes, there are ducts actually which are shown here. So there is no fin efficiency, and also there is no bond conductance or bond resistance, right? So because there are no pipes which are welded to this plate, right? So air is directly coming in contact with this plate, right? So this simplest type of air liquid solar collector, we shall analyze its thermal analysis, but we shall not be deriving all the equations in detail, because there is no time left to derive all those equations. Only 2 weeks left and few weeks left to complete this course. So only we shall study the basic energy balance and the derived equations, which are already derived in the derived forms, are already provided within the book, right? So let's try to understand its energy balance. So the energy balance on the absorber plate is mentioned here first. So here in this type of analysis, we shall be writing the first law of thermodynamics equations or energy balance equations uh, for each component. What is the each component? For the major components are absorber plate, so we shall write energy balance for the absorber plate, then for the glass cover, and also for this back plate, and also sorry, not for the for glass cover there will be no energy balance. We shall be writing the energy balance for this absorber plate, main absorber plate, and the effect of glass cover will be covered in this factor, which is the overall heat transfer coefficient from the top of the absorber plate. So the effect of glass cover will be covered in this term, which is the overall heat transfer coefficient from the top of this absorber plate. So we shall write energy balance for absorber plate, and then we shall write energy balance for this back plate, and we shall also write the energy balance for this fluid which is flowing, this fluid part which is flowing through this duct. So we shall be writing the energy balance for these three components. One, the absorber plate, second is the fluid which is flowing between these two plates, and the third one for this plate, the back plate. And then these three equations, these three energy balances will be solved simultaneously to calculate the heat gain of this air type solar collector. So first of all, an energy balance on the absorber plate is written here. So how we can write the energy balance? So here we are again taking this small area. Let me erase this one. So this small area of this duct is taken, is shown here, right? So fluid is entering here in this portion and leaving with a higher temperature. So entering with the temperature T, leaving with the temperature T plus dT by dx. So here we are taking this small portion of the absorber plate as our thermodynamic system. So this only this absorber plate, I'm showing it separately. So this absorber plate is actually absorbing this radiation S, and the length of this absorber plate in the direction of fluid flow is shown as del X. So here this portion is separately shown here. This is our system actually, right? Not the air and not the back plate or the glass cover. Nothing is our system. Our thermodynamic system is only this small portion of absorber plate at temperature Tp. Right, so now we shall write the first law of thermodynamics equation. So energy entering is equal to energy leaving. So we know the general form of first law of thermodynamics for under steady state, right? So under steady state, that is the energy equation. So energy entering in the form of heat, work and mass must be equal to the energy leaving in the form of heat, work and mass from our system. The system is this one. So what is the energy entering into this system? That is S, right? Watts per meter square multiplied by del X into the length into this slide, and that length is taken as 1, right? So per unit length in the direction into this slide or out of this slide, right? So that is the energy in En, that which is entering into our system. What is our system? That is the absorber plate. And what are the energies which are leaving this absorber plate? So one is the energy, this one, UL, from the same area, del X into 1. And this UT, heat loss coefficient from the top side, due to this temperature difference Tp minus Ta. So when we are saying Tp minus Ta, it means glass cover is included here in this U calculation, right? So that is one energy which is leaving that absorber plate. This is absorbed and that is lost. Second energy which is leaving is from the bottom of this absorber plate, right? Let me show it clearly. There are so many lines, so it becomes difficult to explain, right? So now from this absorber plate, which is our system, let me show it in thick line as thick line. So energy entering is S, energy leaving from the top is UT into TP minus TA. From this area, delta X into 1, and there is energy which is leaving in this direction. What is this energy? This energy is going to this plate by radiation, and also there is energy going to this air, because right under this absorber plate air is flowing. So energy is transferred from this plate to this back plate by radiation, because here we have a surface at a certain temperature, here we have another surface at another temperature. So between these two surfaces there will be a heat exchange due to radiation. That is written here. So HR, radiative heat transfer coefficient from this plate to back plate, P to B, into the area is the same, del X into 1, and due to this temperature difference, TP minus TB, TP minus TB, that temperature difference will derive this radiation heat transfer, right? So that is also the energy which is leaving E out, leaving that system. And that is the third energy which is leaving from the plate to the ambient. From the plate, sorry, not ambient, it is air. From the plate to air. So here A means not ambient, this A means air, right? So that is the convection heat transfer into convection heat transfer coefficient into area into TP minus T, where TP is again the plate temperature minus the fluid temperature, which is air, temperature of the air. So here we are not using subscript A because TA is used for ambient temperature. So that should be clear that here this A represents air, but here this A represents ambient air. This is the temperature of ambient air. So these are the energies entering and leaving our system. What is our system? The absorber plate. So I hope the equation 4.40 is clear now. So in this equation 4.40, there are two convective heat transfer coefficients. One is this one, convective heat transfer coefficient from the absorber plate to air in watts per meter square per Kelvin. Second is the radiation heat transfer coefficient or radiative heat transfer coefficient from absorber plate to this back plate. And UT I already explained. This UT represents all the heat transfers from plate to ambient. So from plate to ambient involves, of course, this UT further consists of two, or actually four heat transfer coefficients. One from plate to glass in the form of radiation and convection, and then from glass to ambient. So all of these radiation and convection heat transfer coefficients from the top of the plate are included in the definition of top heat loss coefficient. Right, so now we shall apply the energy balance on this air stream, this air particle, this air which is flowing. So only air. We are not taking this absorber plate and back plate included in this air. So now the our system is only this air or the fluid which is flowing, right? So this fluid is now exposed to certain energies. Now we shall apply the same energy balance, E in is equal to E out, to only this air pocket, right? So this air is actually receiving heat from this plate, absorber plate, right? And this air is also absorbing heat from this back plate, right? This back plate and absorber plate both are actually transferring heat to this air, because that is a metal surface, that is a metal surface. So both of these plates are actually giving heat to this air. So the heat going into the air is actually convection heat transfer coefficient from the top plate and convection heat transfer from the bottom plate, right? And what air is doing, for example, here in this system, this air is entering because that is an open system. Air is entering, air is leaving from this system which we have defined as air. So here fluid is entering with the energy mcp into T, and it is leaving with this temperature change mcp into T plus this differential change in temperature of this air from T to T plus dTf dt by dx into del x. So that represents the differential change in temperature of air. So the net heat gain of this air is given by m dot cp into, okay, now what is this term? I can write it here. This term is actually this was mcp at the inlet, right? And after gaining this heat from the top of the plate and from the bottom of the plate, its temperature is increased. So this change is d plus dt by dx into del x, that is the temperature of this air when it leaves this element del x, right? That was the final temperature. And what was the initial temperature T when the fluid was entering into this element of length del x. So this T will cancel with this T, and this whole term is actually multiplied with mcp. And what is m dot divided by w? Here we are taking per unit area के form में. So per unit W, the width of this solar collector, right? So I hope this term is clear. That is the energy gain of the fluid, right? Or energy with which the fluid is leaving this element of length dx. This air has gained this much amount of heat, and from where it has gained? From here. So that is the energy in to this element of del x, and that is the energy out of this air. This air is leaving this element del x of length del x with this energy. Which energy? This one. That represents this change. Here this term is actually this term T plus dtx by dx into dx minus T. This T is cancelled with this T, and what is remaining is this term which is written here, m into cp. Everything is written for unit length, so that's why it is unit area or unit length, so that's why it is divided by W, right? For a certain width of that solar collector, the total width will be the total W in the direction into or out of this this slide. So if this equation is also clear, this is the energy balance on air stream, which is present in this element del x. For the same element del x, we wrote this equation for the energy balance for the absorber plate. Similarly, now we shall write the equation for the back plate, because back plate is also losing heat in this direction, and it is giving heat in this direction to the air, and it is absorbing heat from the top absorber due to radiation, right? So now we shall write equation for the second or the back plate, the second plate. Okay, so this is clear, where HCBA and HCPA is already explained, right? Now we shall write the energy balance on back plate, that is the back plate. So now this back plate is our system. Now this back plate is the system, our thermodynamic system, on which air, some energy is entering. What energy is entering here? The radiation heat transfer from this heated absorber plate to this one. So that is HR, from plate to back plate, from a main absorber plate to back plate. That is the energy entering. And there is no other energy entering into this back plate. So what is the energy leaving? Energy leaving from this back plate to this air, right? From this back plate to this air, and from the bottom of this back plate to the ambient, which is represented by this overall heat loss coefficient. So again, En is equal to E out. So that is the En, radiation heat transfer from plate to back plate for the same area, del x into 1, and due to this temperature difference, Tp minus Tb. So that is the energy in, and that is the energy out. HCB2A del x into Tb minus T plus UB, that is the energy leaving from the bottom. So that is the third equation. So now here we shall see that normally its bottom heat loss coefficient is negligibly small compared to this top heat loss coefficient. So here we can say that the overall heat loss coefficient is simply given by UT if we neglect UB. So if in this equation we neglect this UB, means this term is negligible, approaching to 0. And now we can write the equation of TB from this equation 4.42. What is 4.42? That is the energy balance on the back plate. So here is equation 4.43. Now we shall not be doing any mathematical steps. The intermediate steps you can perform by yourself. So here we have written the equation in terms of TB from this equation 4.42. Now what we will do, we will substitute this equation in equation 4.40. What was equation 4.40? The first energy balance which we derived here for the top plate, for this absorber plate. So here the same TB is replaced here, right? The back plate temperature equation, because normally back plate temperature is not known. So we are replacing this TB from the equation of this back plate here in equation 4.4, right? And so this equation is 4.40. We have substituted this TB from equation 4.42 in equation 4.40, and then after doing a number of mathematical steps, that is the final form which we will get from equation 4.40, right? So here in this equation, this H, only H, is actually this term, where HCPA is convection heat transfer from plate to air. HCBA is convection heat transfer from the back plate to air. No, it's not ambient, it's air. And this third one is radiative heat transfer from plate to back plate, from plate to back plate, right? Okay. So next what is done here, substituting equation 4.43, the same equation, TB equation. Initially we put this equation 4.43 in 4.40, which was the equation of this absorber plate, 4.40, and then after doing certain mathematical steps, this was the equation which we derived. Now the same equation 4.43 is now put in this equation of air, here for air. The equation, the energy balance which we written for air, that was equation 4.41. So now we shall put the same TB equation. Initially we put it here, now we shall put here, that is the equation 4.41, right? So, and then we shall get this after substituting equation 4.43 in equation 4.41 gives this equation. Here the same H is actually given by this term. So the mathematical steps we shall not be doing. We shall be only using these equations to solve the numerical problem. So now we have this equation 4.44a. So now this equation 4.45, which was actually the combining equation, this 4.44 and 4.4a, these two equations 4.44 and 4.44a, which we have derived after putting TB, backplate temperature, in the equations of main absorber temperature, absorber plate, and the equation of this air, the working fluid, right? So, and then we get these two equations. And now after solving these two equations, right, simultaneously we get this equation, right, 4.45. So the derivation steps are missing here, and those are not included because we do not have time, because we still want to study the concentrators. So that's why here the derivation steps are not included in the course, but you still need to understand each term separately. So here we, after doing a number of algebraic steps, this equation 4.45 is derived, and here we have, just like in liquid flat plate solar collectors, we are defining this term. We have introduced this term f dash. And what is this f dash? This f dash is given by this equation. So this derivation is not included or not mentioned here. But now we have a similar equation as we had for liquid flat plate solar collectors, but here f dash is given by this equation, where h, I already told you, h is this one. This h is actually given by this equation, right? So now we can solve this differential equation, because it involves dt by dx, changing temperature in the x direction, that is the x direction. So the dt, temperature change in the x direction, represents this dt by dx. So now we can solve this equation by utilizing the initial conditions. What are initial conditions? At the inlet, temperature is Ti or TFI, which is normally known to us at x is equal to 0. This is x direction. So this represents x is equal to 0. At x is equal to 0, what is known? The initial condition which is known is that temperature is equal to Ti, inlet fluid temperature at x is equal to 0. So then solving this equation, differential equation, will give us this equation, that is the temperature of the fluid in x direction. So by solving this equation 4.45 using this initial condition, and after simplifying, that is the equation which we get, that represents the temperature of air at any x. X is the flow direction in this case. This direction is x direction, right? So where Ti is the inlet fluid temperature, UL is the overall heat transfer coefficient, which we have assumed UL is equal to UT by neglecting UB, right? So the rest of the terms are very much clear to you, where f dash is this one, where f dash is further equal to this term, and we know h is not a simple h, it consists of three h's, which we have already discussed in the previous slides, right? So that is the equation 4.46. The complete derivation is again a few hours work, which we have not included. So that is the temperature of the fluid at any x, or this equation gives the temperature, can give you the temperature distribution in the x direction. Similarly, now we can apply the another boundary condition, that was the one boundary condition at the initial state, or at the initial position. Similarly, when this fluid is leaving this absorber plate or leaving this solar collector, so then temperature will be TO, means at x is equal to L. So this is x direction, and the total length in this direction is, for example, L, and in the direction into the slide is the length of the solar collector is given by W, right? So at x is equal to L at the exit of the solar collector, what will be the area? The total, now the fluid has flown through this whole area of the solar collector, which is given by W into L. W is in the direction into this slide, into this length L, the flow direction. So at x is equal to L and AC is equal to WL. So the same equation can be written or the same equation can be derived for the outlet fluid temperature, TO is equal to Ti plus. So the overall procedure is quite same, which we have already done in the liquid flat plate solar collectors. There also we have derived similar equations of estimating fluid temperature in the x direction, or temperature distribution equation in the x direction, and the final temperature of the fluid when it is leaving at the end of this solar collector, when it flows through this whole area AC, right? So again, there are a number of steps, mathematical steps involved, and the final equation is only shown here, which gives the final temperature TO. Right, so the energy gain of this air stream is now given by QU divided by per unit width is equal to m dot per unit width into Cp into TO minus Ts. So the overall heat gain of this fluid when it is entering here and leaving from here, the total temperature change is from Ti to TO. So m dot into Cp into this delta T, that represents the total heat gain, and here we have written for a unit width, right? That is length direction, and width direction is into this slide, right? So that is actually given by this equation, right, which we have already derived for T naught and Ti. The equation for T naught minus Ti, so that is the equation 4.48, which is derived from 4.47. So here actually in this equation we have simply replaced T naught from equation 4.47, the equation 4.47. We put that equation here of T naught, and then after simplification, that is the final form, which is actually the useful heat gain. So that is the equation 4.48, which represents the, here we can introduce the heat removal factor just like in liquid flat plate solar collectors. So here this whole term represents FR. So here we can simply say that this term into this whole term, this one, that is actually, we can say it is FR. So that is the simplified. So here this, replace this whole term with FR into AC, the collector area, into S minus UL into Ti minus. So that is the same general form of energy balance which we have used in liquid flat plate solar collectors also, and where FR is this whole complex term, right? So here we can say show separately. So we can simply show the energy gain of air type solar collector with this equation, and in this equation this FR is written here, right? Now in this FR we have this UL, which is actually UT, and also in this equation we have this F dash, which is a complex function of so many parameters, this F dash, right, which is given by H over H plus UL. UL is the same U, this one, and H is further, we have already discussed this, H represents distance. So this equation, this final equation in terms of FR is our required equation, but this FR is not easy to calculate. It has involved the effect of all the parameters or the design parameters which are affecting the performance of that solar